So in this problem, we're going to be doing a combined spectra problem. So we're given the molecular formula, we're given an IR spectrum and a proton NMR spectrum. And from all that information, we can put that together to create and identify the structure of our unknown. So when we're given this type of problem, the first thing that we're going to want to do is to do the HDI. So we're going to figure out how many pi bonds and or rings exist within our system. So that equation looks like this. So we have, the equation is 2 carbons. So 2 carbons plus 2. We're going to subtract the number of hydrogens. We're going to subtract the number of halogens. So that's our group 7 elements. So fluorine, chlorine, bromine, or iodine. And then we're going to add the number of nitrogens. Importantly, we exclude oxygen, or we do not include oxygen within this calculation. And we're going to take all of that and divide it by 2. So for our equation where we have C5H10O2, we're going to have 10 plus 2, and we're going to subtract the 10 hydrogens and divide that by 2. That's going to get us to an HDI of 1. So we have either 1 pi bond or 1 ring within our system. Next, we're going to take a look at our IR spectrum. And we take a look at our values here. Actually, this value is a little bit off. So based on the value here, it should be 2945. But the important part is that these two are the same in terms of our identity of the type of bond. So we can look and identify that these are below 3000. So this grid kind of helps us look at that 3000 line. And we notice that all of our signals are below 3000. So if we're below 3000 in that hydrogen region, we have a carbon-hydrogen stretch in which the carbon is sp3 hybridized. So carbon sp3 hybridized with a CH stretch. So again, that's important. So ultimately, we don't likely have a carbon-carbon double bond that has a carbon-hydrogen attached to it. The only other piece of information from our IR spectrum that is in our diagnostic region or above 1500 is this peak at 1740. So it's a very strong peak, occurs within that double bond region, and it's between between 1750 and 1680 or 1700. So this corresponds very strongly to that carbonyl stretch, that carbon-oxygen double bond. And again, that makes sense in the context because we have an HDI of 1. So that ultimately, we know that we have a pi bond existing within our system. So we've extracted as much information as we can from our IR spectrum. So now let's go ahead and focus on our proton NMR. So we're given some information already. We're given the chemical shift and the integration. So now what we need to do is figure out the multiplicity. Again, that's telling us how many adjacent hydrogens there are to the chemical signal. And we can figure out the multiplicity by simply looking at the shape of the signal. So if we take a look at our most de-shielded signal, so the one at 4.15, if we simply count the number of peaks here, we have 1, 2, 3, and 4. So that corresponds to a quartet. So we have a quartet at that position. If we look at the peak at 2.32, we have 1, 2, 3, 4 peaks. So we have another quartet. And we have 2 additional peaks that are fairly close to each other, but they are, within a different chemical environment, so we can identify their multiplicity. So the one at 1.34 is going to be a 1, 2, and 3. It's going to be a triplet. And the adjacent signal is also a triplet, so 1, 2, and 3. Okay, so now we've identified the multiplicity or the splitting of each signal. So again, that helps us know about the adjacent environment to that chemical signal. So from here, what we need to do is figure out the partial structures. So if we're stuck trying to figure out these partial structures, the place that I like to start with is the one that is the most shielded. So the reason why I like to do this is typically the signals that are the most shielded are the ones that are furthest away from the functional group. And we might have some idea based on the IR spectrum what that functional group is, but ultimately, again, we can sort of piece this together. So we'll start at the end of the molecule and work towards the middle. So based on this, based on the chemical shift and based on the integration and the multiplicity, I'm going to have a signal that has 3 hydrogens, and it's going to be attached to a atom that has 2 hydrogens. And then I don't necessarily know what's on the other end here, but again, just going to indicate the fact that I'm going to circle the 3 hydrogens. That's the signal that I'm talking about. Again, it sees 2 adjacent hydrogens plus 1. That's going to get me to my triplet, matches the integration that we're given. The signal that is above this, so 1.34, looks very similar, right? I'm going to have, again, a integration of 3. And that's going to be attached to a carbon atom that has 2 hydrogens as well. And so ultimately, we're going to have roughly the same partial structure. Notice that these do have different chemical shifts associated with them. So they're going to be attached to something different on this far right-hand side. So let's talk a little bit about what it might be attached to. So I have a carbonyl, and I also have another oxygen present within my system. So based on the fact that I only have 2 additional signals, likely what's going to happen is this carbon-oxygen, again, we can think about parts of a structure that, if they are adjacent to a signal, are going to have essentially no hydrogens. So our carbonyl, again, is going to have no hydrogen signals. So again, if I have some sort of signal attached to it, it's not going to see any hydrogens on that carbonyl carbon. We also have an oxygen that is also a no hydrogen signal as well. So again, if something is attached to it, it's not going to see any hydrogens on that oxygen. So in this case, I only have 2 remaining signals, and based on the integration, those are going to be CH2 values. So it's unlikely that I have a signal between my carbonyl and my oxygen. So with that in mind, what's going to happen is I'm going to merge these 2 together and create an ester functional group. This makes sense in the context of the chemical shift of the remaining signals that I have. So notice I have a chemical shift at 4.15 and then one at 2.32. Notice that there's almost a 2 ppm difference in the chemical shift here. So based on this, I know that this signal with its 2 hydrogens is going to be adjacent to that oxygen, to that more electronegative oxygen. So what this looks like in terms of the partial structure is going to be my ester with the oxygen, and that's going to be my CH2. So again, that's my signal that I'm talking about. And it's going to be adjacent to a CH3. The reason why I know it's adjacent to a CH3 is the multiplicity. Again, I look to the left, it sees no hydrogens on this side here, it sees 3 hydrogens plus 1, that gets me to my quartet. So this is the one side of the ester. On the oxygen side of the ester, I have a fragment on the other side of my ester. So if we think about the carbonyl, we're looking at the other side now, and now I have a CH2. And again, based on the integration, there's 2 hydrogens there, and we know that that's going to be attached to a CH3, again, based on the multiplicity of a quartet. So it sees 3 hydrogens on the left-hand side, sees no hydrogens at the carbonyl position. So ultimately, here are our partial structures, and really what this breaks down to is our 2 partial structures here are 2 ethyl groups, and they are on either side of my ester. So again, I have my ester functional group with the oxygen, and I have a ethyl group coming off one side of the oxygen, and I have an ethyl group coming off the carbonyl side of the ester. So one thing that we want to do whenever we draw a final structure, we want to make sure it matches our molecular formula. So I'm going to go ahead and draw in all of the hydrogens that exist at each of the carbon atoms, just to again confirm that we have the correct number of hydrogens. So if we were to add this all up together, we have 3 hydrogens plus 2 is 5, another 2 is 7, plus 3 is 10. So this practice problem came from a subset from the Colorado University at Boulder. So if you want some additional practice problems, feel free to follow this link. I'll post the slides, so follow this link. There's 20 practice problems to work through. So again, feel free, if you need some additional practice, work on those as practice problems.